motion.
Yeah, for
And then for the sphere, I haven't done it, but the volume of sphere minus the cylinder of the sphere, right? So for the diameter, I got 0.5, 2.2, 3, or the 9.4. Yeah. How did you do the math for the triangle? Because I saw two different formulas. I saw the base times height times length times half. Okay, cool. Okay, cool. I'll do the math. I just double checking it because I was rewriting it today. I was like, wait a minute. Yeah, okay. It's not good.
So we got all the average values. We plotted the path of the particle, and then we also started plotting the graph of the position versus time. And then we have velocity versus time. The velocity was the first one we graphed, I think. -3 to 3. This is time, and this is the velocity here, and then the speed was the absolute value of that. Speed. And the acceleration was a linearly increasing function, so that one was A of t and then the position one was 1. I think we were kind of at the stage where we were going to do the position as a function of time, Q. Okay, so we have this one. We know that it starts at x equals to 1, and then at x equals to 3, it ends up at 8. So it looks something like this. Now, if we wanted to be careful about the concavity of the position versus time, we could look at the second derivative of position, which is acceleration. We can say, okay, the second derivative of the position is negative, then it's concave down. So that's the acceleration. right? So you see here that mostly the acceleration is positive, except for a little portion where the acceleration is negative, then that one's concave down. So if you look at the acceleration function, you can see that at t equals to 1, the acceleration is 0, right? So then from here to 1, the acceleration is negative. Then after that, the acceleration is positive. So the concavity of this is going to be concave down up to that point. Then over here, there's an inflection point. So that then from this point on, it becomes concave up. Concave up, concave up. And you see here, it's concave up. So it doesn't go like this. It doesn't go like that or something. You know, there's no other inflection point. So it's just gonna keep going. That's nice. Okay, now we can show the meaning of these values, the average values on those graphs. So the speed average is gonna be on this one, right? The average speed in stage 1 is, was that 3 meters per second? That should be the average height of this function, right? From here to here. Something seems wrong. Was that really? The average speed here was 3? Because how is the average height of this 3 if it starts at 3? 0, -3. Because the average height of this should be somewhere between 0 and 3. I don't know, is that right? So this is the kind of stuff that you have to ask yourself, you know, when you're solving it and then when you're graphing that. Doesn't sound right. If we go back to how we solve these things, we can check how did we do that. Remember we drew the path of the particle. We said that the particle starts at 1 at t equals to 0. Its initial velocity was -3. V1 initial, -3. And it goes at t equals to 3 seconds, it stopped, right? At -8. So at t equals to 3 seconds, then it goes like that. And by t equals to 5 seconds, it gets to 2.667. So t equals to 5. The final velocity of the object was 12 meters per second. V final stage 2 was 12 meters per second. V initial stage 1 was -3. So how did we get the average speed is 3? We took the distance over the time, and the distance was 9 over time is 3 meters per second.
You can have the velocity function right now. Over example. We are 1, t equals 1.
What is it?
The velocity function.
Is wrong?
Yeah.
That it doesn't start at -3?
I mean, it goes down from -3.
There you go, yeah. So you see, something is not matching. Something is not matching. And that's exactly it, he got it. This has to go down and then back up. And we weren't careful when we graphed it. Yep, exactly. So why is it going down? Well, because the acceleration is negative from 0 to 1 second, right? So initial acceleration is initial is negative 2 meters per second squared. Well, if your velocity is to the left and your acceleration is to the left, that means the car is speeding up. Or if it's a particle is speeding up. So if it's speeding up, your velocity should be getting more negative now. You see? Now at the instant that you reach acceleration of 0, that's when you reach your highest speed, going to the left. So what we can do now is take t equals to 1 and put it back into the v function. So v of t equals 1 is going to be 1 minus 2 minus 3. That's going to be negative 4 meters per second. So this is now negative 4. Then it slows down, right? So, okay, now we got it. It goes like this. This is all the graphing techniques that you learn in Calc 1, right? So let's do, this is 1, this is 2, this is 3, this is 4, this is 5. Okay, good. Which means if we do the speed should go from 0 to 4, then back down. That was kind of tricky, huh? Well, now that we can say, okay, average speed in stage 1 is 3, makes sense. So the average height of this function can now be 3. But if it was simply going down, it can't be 3. You see, we caught that error. Okay? Okay, so now we're going to say the average height of this function from 0 to 3, S average 1. That's 3, okay, and then S average 2 is 5.33, which is here. And then S average total is 3.993, which is going to be somewhere here. S average total. See, so S average total is going to be slightly below the highest velocity, which was 4. So a lot of little nuances here that you have to do when you're drawing it nicely. This is 3, this is 3.993, and then this is 5.33. Okay, now let's do the V average. On this graph, we can show the graphical meaning of V average 1, negative 3. From here to here, V average 1. Okay, then you're going to do the V average 2, 5.33. And then the V average total, which is 0.33. So that's quite different than the S average total. 0.33, that's going to be just barely above the x-axis. V average total. Now that makes sense because the average height of this function, because you got negative, right? And then you got positive, but this period that is positive is less than the time period that it's negative. So overall, the height of the function is barely positive, which what that basically means is that the displacement of the car is barely to the right, just barely to the right, okay? Now we're gonna do the meaning of the average V's on the X graph. Okay, so on the X graph, how do we show the average V? Not by doing heights, but by connecting the beginning and the end point, right? So the first stage from 0 to 3, connect it with a secant line. Take the slope of that, and that is the V average 1. Which is the negative 3. So you see here you do it by taking the average height. So here you do it by connecting the line, and then here to here, connect the line. Take the slope of that, that's B average 2. So it should be making sense again. When you compare these to your answers, they should be matching. The first slope is negative, the second slope is positive, and then the overall slope is the secant line from the start to the end. Well, notice that it's slightly inclined upwards, which means its slope is slight positive. The average total. So V average, that's negative, positive, and then very slight positive. See? So these numbers together with the graphs help each other check out to see if it makes sense. Then the next thing to do is on the A graph, show the graphical meaning of the A average. So A average 1 is 1, so that it's from 0 to 3 is the first stage. So the A average 1 is just 1. That one is kind of easy to check because the acceleration is a linearly increasing function. When something is a linearly increasing function, what is its average value? It's the midpoint of the two ends, right? It's the literal midpoint. You can't say that about this kind of function because it's not a linear function. It starts at 3, then goes to 4, then ends up at 0. Well, what is its average value? You don't know. You have to integrate it, right? But here, if it's a linearly increasing function, I can take the midpoint of 4 and negative 2, which is what? 4 plus negative 2 is 2, divided by 2 is 1, right? So you just basically take the average, 4 plus negative 2, and that's going to be 2 over 2, which is 1. And that is the average A. See, that's a different way of getting the average A than the way that we got by taking the V final minus the V initial. But this way of doing it only works if it's a linear function. See? Then the average A in the second stage would be 6. So that's 4 and 8, right? Because midpoint is 6. And then the total average A is 3. Which is the midpoint of negative 2 and 8. That's 3. Okay? And then the last thing to do is to show the average A's on the V graph. Okay? And then how do we do that? Well, on the V graph, the A is the slope of the secant line again. So from the start to the end of the first stage, connect it with the secant line. Slope of that, A average 1, which is your 1. See? So a slight positive answer, which means it's barely positive. Then from here to here, slope of that, A average 2, which is a steep line. And then from here to here, A average total. So now if you did it right, this one should be the least steep, which is 1. This one should be steeper, and then this one should be in the middle, which is the 3. And none of them should be a negative, right? Because there is no downward sloping line. Now this one is a negative slope, and we did get negative, you see? So it's a very interesting thing where you're basically mapping what something is doing. Literally, you're just taking somebody. It could just be me walking, you know, and then accelerating, stopping, accelerating. Take a random walk of a person, analyze those, get average values, and then plot the stuff, and then apply what you know from calculus to that plot, and everything should match. You see? Okay, cool. Okay, now let's take a particular category of accelerating motion, and that's known as acceleration with constant acceleration. Okay? Now, the case we did here is acceleration where the acceleration is changing, but it's changing at a constant rate. So, in other words, the derivative of an acceleration is constant in this case, right? But the acceleration itself is not constant. It's a variable acceleration. You see? So the derivative of the acceleration here, dA dt, anyone that would know what that's called? Derivative of acceleration? Jerk. So we can call it J. So every time someone calls you a jerk, just say, oh, that's good, I'm a jerk. You know, I'm the derivative of acceleration, and they'll go, you jerk. I'm the rate of change of the rate of change of the rate of change of position as a function of time, right? So in this case, the derivative would be 2, right? Which would be like this. So J as a function of time, 2. Jerk is somewhat essential when you're designing like roller coaster rides. You don't want the jerk to be too high, you know. So you don't want the force felt by an object, by a person. You don't want that force to change too fast as a function of time. You see, so you want to keep the jerk to minimum, because then that's what gives you whiplash and stuff. So you want the acceleration to be kind of low, and you want the change of the acceleration to be low, right, in roller coaster rides. So, but in most instances, we don't really deal with the jerk too much, because as far as physics is concerned, usually the second derivative of the something is the where you stop. It has physical meaning. In other words, you have position, you have velocity, which is the first derivative of position, and then you have acceleration, which is the second derivative of position. And then acceleration is equal to F force over mass. But the derivative of acceleration, there's no equation that uses that. Okay? Now it might be good for design purposes, for engineering design purposes, but the physics doesn't use that per se. And when you get to physics 3, you will notice that the same thing is important in physics 3. You have, instead of position as a function of time, you will have charge as a function of time. And the stored charge is necessary in capacitors. So when you have a battery, you store charge on the capacitor, right? And then you close the circuit, you store charge, and by storing charge on a capacitor, you store electrical energy. So then we can plot the charge of the capacitor as a function of time, something like this. Asymptotically, it increases until the capacitor charge. If you take the derivative of charge, you get current, the current in the circuit. And so the derivative of this is going to be something like this. So where's current important? That's if there is a resistor in the circuit. Then current is important, right? Because the voltage drop across the resistor is the current times the resistance of the resistor. See? Then if you take the derivative of current, you get something known as di dt, and that's the derivative of this guy. So since this is negative, the derivative is going to be like this. And when is the derivative of current important? That's when there's an inductor in the circuit. See? So inductance relies on the derivative of current. Resistance depends on current. Capacitance depends on charge. Charge is to position. current is to velocity, and di dt is to acceleration. See? Now, if you take the second, one more derivative of this, you might get something, call that whatever, you know. But again, no one uses that much. You know, we can call that electrical jerk. Okay. So yeah, you have very equivalent stuff like that in electricity, and everything maps. Mechanics maps into electricity. You know. So in the next cases that we're going to do cases where the acceleration is constant. So if the acceleration is constant, what's going to happen to the jerk? Then the jerk becomes 0, and the acceleration becomes a horizontal line. You see?
Professor,
Yes.
I was just wondering, for DIDT, wouldn't that be helpful if we're running off, let's say, batteries, and if it's pulling too much at one point, like it drains the battery too fast, wouldn't that be useful?
Yeah, the rate of change of the current.
Like if it a very quick, high amp draw,
Yeah.
that's what we would kind of use.
Well, actually, that just would be the current itself.
Oh, okay.
You're drawing too much current from the battery.
Right.
But the DIDT mainly matters if you have an inductor in the circuit, which is a coil.
Okay.
Yeah. So now you have cases where the equations of kinematics for constant acceleration. So that means the acceleration as a function of time is some constant number, right, horizontal line, but it could also be some constant negative number. So either some constant positive or constant negative, which means the jerk is going to be 0, right? Now, how is the velocity going to be? The velocity depends on if the velocity starts out positive, right? So you can, because remember, velocity is the integral of acceleration. So the general equation for v is going to be integral a dt, right? So then you're going to have here, if a is constant, then a can come out of the integral. Then you have here a t plus a constant. So that literally means if the acceleration is constant, the velocity is a linearly increasing function, or it could be a linearly decreasing function if the a is negative. And then the constant is the initial velocity. So we have here v is equal to at plus v initial. So that gives us the first equation of objects with constant acceleration. V final is equal to v initial plus at. That's known as the first equation of kinematics. But kinematics for constant acceleration situations, right? So that means if you have v initial is positive, if the object has a positive acceleration, it's gonna go up, right? Because the slope of this is the acceleration. Or it could go down if the acceleration is negative. Okay? Or the initial velocity can be negative. Right? So you can start at any initial velocity. The constant can be anything that it wants. So what if you start at negative? Then if the acceleration is positive, or the acceleration is negative. So you literally have 4 cases that could possibly happen. V initial positive, A positive, V initial positive, A negative, V initial negative, A positive, and V initial negative, A negative. Now say, give us situations, when would this happen? You know, when would any of these 4 happen? So it's good to visualize them. one of the best scenarios we can visualize is throwing a ball up or throwing a ball down. Right? So if you throw a ball up, throw a ball up, V initial is positive, and then A is this way, right? Negative 9.8. So that's gonna be like this case. No, like this case, right? V initial is positive, but the A is negative. So at some point, it's gonna stop when it crosses the x-axis. See? Right there. So it's gonna go up, slow down, and go like that. You see? So that point is the graphical interpretation of this point, right? Right there. That means it reaches its maximum height. Okay? How about if you throw the ball down? The initial is negative, but A is also negative, right? And then that's gonna be this one. It goes down. So it never goes up. So it never stops, right? So with the freefall problems, we can mimic this situation. Throwing a ball, this is throwing a ball down. This is throwing a ball up. Okay? How about something like this? As you are throwing, the ball is in your hand. Let's say this is a ball. Okay? How about the physics of what happens while the marker is in contact with your hand?
The acceleration.
Not when you let go. So you gotta go like this.
Acceleration is
You
positive.
see? So during that period when it's in your hand, you're giving a force, enough of a force to beat the acceleration of gravity, right? So it's actually accelerating up. So in that case, we're able to do this. You see? The initial is positive and the acceleration is positive. So we mimic this scenario right here. So this is throw a ball up while it's in your hand. So what happens while it's in your hand? The velocity is increasing, increasing, increasing. Then at the moment that you let go, what happens? Let's say you let go like right there. Then this equation takes over, right? It goes down until it finally stops. You see? So while it's in your hand, this is happening. The instant that you let go, this is happening. So notice, as soon as you let go, it's still going up. Why? Because it had a certain velocity right here, you see? Then it takes time for the velocity to drop to 0, and then the object turns around, you see? And then you can also do the same thing with throwing something down, right? While it's in, again, contact with your body, you're accelerating.
But it's still going
But that one
down.
is still going to be this one, right? How can we do this one?
For example, like if there's wind or anything like going up, there's wind. When you throw something down and there's wind like blowing up.
Oh, okay, yeah. To mimic that, it's a little bit harder. You have to throw something down, but the acceleration is up. Oh, how about if you get a helium balloon? You're at a birthday party. You get a helium balloon and you just go like that,
Yeah.
right?
Yeah.
Still going.
You get pissed off at your daughter or something. Why did you do that? And then the balloon goes down, right? The balloon goes down, 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 but it's slowing down, right? then it's gonna stop, then the balloon is gonna keep going up after that. So that one is, you have to get something that's maybe lighter than air, so that it turns around.
Or be underwater.
Or be underwater, yeah.
You have two of those. Were this in VI and the bottom?
VI is the whatever initial velocity that you give it. VI is V initial, V initial. It could be positive or negative.
Oh, I see.
Yeah. And acceleration can be positive, negative, positive, negative. But this equation could take care of any kind of possibility, any kind of case that you have, okay? Now, if you want to get the function of position versus time, then you integrate this one more time.
But I have another question.
Yes.
How does the initial negative start?
How does this start?
Yeah, like,
If you throw the ball, throwing a ball down.
like initially, how does it look? Because it's negative velocity initially. So if I was gonna like have an example, how would I?
Throwing a ball down.
But
That's
start-
you're giving it an initial velocity.
It starts off at negative. I thought it was gonna be zero. So that's why.
Direction.
Oh, I see. How do you start at a negative, you're saying? Yeah, because if you, well, when it's in your hand, it's zero. Then you accelerate it down, so it literally starts like this, kind of. It starts like this, but then this is still while it's in your hand. Then you let go over there, then the acceleration of gravity takes over. It could be like this or like this. So this is the acceleration you give it. Then you let go, and the instant that you let go, the acceleration of gravity takes over. So depending on how fast you were accelerating, gravity could be steeper or less steep. Most of the time, you're probably gonna give it an acceleration maybe faster than gravity, right? So you're gonna speed it up, then after that, gravity takes over. Yeah, I know what you mean, like how did it start negative? Yeah. That's why this chapter is important, that you also graphically can interpret graphs like this. So you can visualize, okay, what's the physics of that? What's the situation is that mimicking? Okay, now the integral of that is gonna be, v is gonna be dx dt, which is gonna be v initial plus at. So dx is gonna be v initial plus at dt. And integral x of t is gonna be v initial t plus half at squared plus a constant. So this gives us the velocity as a function of time equation. X final at a constant is going to be the initial x. And then this is your v initial t. So x initial plus, literally basically it's like the integral of this. So if you integrate this, you're going to get v initial t. Then the integral of that is going to be half at squared. That's your second equation, right? Half at squared. Now to get the third equation and the fourth equation, these two equations are the most often used ones. But if I want another equation where the t is eliminated, I can take this substituted for t, and then I can factor it in here and factor it in here and get rid of t. And this gives you the little bit less often used equation. V final squared is V initial squared plus 2a x final minus x initial. So basically I've gotten rid of the variable of t in there, okay? So each of these has an advantage. This one has an advantage that it's missing V final. Missing V final. This one is missing t. And then there's a fourth one that is like this. X initial is, X final is X initial plus V initial plus V final over 2t. And this one is missing the what? Missing A itself. So you don't need to know what the acceleration is. But of course it only applies for constant acceleration. Once you know that there's a constant acceleration, you can use this equation, but you don't need to know the A itself. So how do you derive this? You take A, you substitute for A, right? So you solve for A is V final minus V initial over T, then you substitute that A into here, and then you eliminate the A. Then this is what you're gonna end up. Okay, so in all of the kinematics equations, you can use this. And then the graph of x of t versus time is going to be looking something like this. And then here, of course, you again can get many cases. You can have x initial positive, which means it starts here. So if it goes like this, right? So that means this object is initially going to the left, right? Initially going to the left, slows down, stops, and then keeps going to the right. Or it could be something like this. This object initially is going to the left, but it's speeding up, and keeps going to the left forever, you see? Or it could be something like this. This object is initially going to the right, and then stops, and then goes to the left. So in many different cases, depending on what your initial velocity is, right? Depending on the initial velocity. If the initial velocity is positive, it's gonna be like this. The initial velocity is negative, it could be like this or like this. So it also depends on what the A is, right? It's kind of like the mathematical equivalent of saying you have many different kinds of parabolas that you can get. Upward opening parabola, downward opening parabola. So all of these equations are parabolas. So it just depends what's happening to the problem, whether it's upward opening, downward opening. That's x initial, exactly. And you can even have sometimes x initial negative. So you can have a downward opening, then it goes up. You can get like this, you can get like this, you can get like this. Literally, you probably have like this, upward opening, upward, down, down. I think you have 4 and another 4, so you have possibly 8 such scenarios that can happen. Okay, so let's practice one of these kinds of problems. So car is going to the right at 60 miles an hour when it notices a slow-moving car ahead of it by 120 feet, moving at 40 miles an hour. You immediately press the brakes to slow down. What should your deceleration be so that your minimum distance of approach is 15 feet between you and that car? So this is a pretty practical problem. Happens on the freeway a lot. You're moving and you get annoyed by the guy in front. They're moving slow. So you look at the lane to your right and left, let's say, and they're all full. So you have to slow down. So how fast should you slow down so that you get the closest approach? So always have your TIs handy when you're driving. Do this calculation. That's it. You're safe. Now, if we wanted to do this without any of the math and equations, what would the graph of this look like? Let's see, you have two cars, right? One car is moving to the right at 60 miles an hour, and then he's gonna start to slow down, right? So his initial velocity is positive, but he wants to slow down. Does he want to slow down and turn around, or what? No, just slow down to the point where he's moving at the same speed as the other car, right? That's your only goal, not turning around. So what is your graph gonna look like for the car, for this car A, and then this is car B. So what's that one? So it's probably gonna look something like this. At first you're going very fast, so this graph starts out steep, then you're gonna decelerate. Okay? And then so eventually at a certain time, let's say you have reached the speed that you want to reach. After that, you can go at constant speed. You see? So that's x as a function of t. This is t1, let's say. What's the x of the car B look like? This is x of car A. X of car B, originally he is what? 120 feet ahead, which means their x initial is 120. They're going at constant speed, so their speed is what? Well, their speed is the speed you want to achieve, which means they're going like this fast. You see? So at this point is when you have achieved your goal. You see, your distance is getting shorter, 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 and then at that point, let's do something like this. You see that? So you're slowing down, which means the slope of the tangent line is decreasing. Right? And at the point where you reach the same velocity, now your velocity is what? 40 miles an hour, right? And then this is also 40 miles an hour. And after that, your distance always stays the same. So these two lines are parallel. Nice, I love that. So when you're braking, this is the graph you should have in mind. You should have this picture in mind. Visualizing like that. Right? So how do we set this up? We can change this to, since this is feet, change this to feet per second, and then change that to feet per second. 60 miles an hour is an easy one to remember. It's 88 feet per second. Because 1 mile is 5280 feet, right? And 1 hour is 3600 seconds. So if we multiply this by 5280 over 3600, we get 88. So then 40 miles an hour will be what? 4/6 of 88. Because if 60 is 88, 40 is 4/6 of 88, which is going to be probably a fraction, right? Some decimal. $58.6667. Okay, so then, how do we set it up? We want the closest distance to be 15 feet. So that means we want this thing to be 15 feet, right? How do we set it up? What do we do? How about if we use this equation to say,
You can get an acceleration.
you could say, okay, we don't have the acceleration, but we could say V final is V initial plus AT. So V final, you want it to be 58 point, you want the final velocity of car A to be that, right? 58.6667. V initial is 88. So that means that the acceleration, it just gives you a relationship between the A and the T. You should accelerate at such a rate that the time that you are decelerating times the acceleration is the difference of these two, right? Which is going to be so AT is negative 29.333, right? In other words, the acceleration that you're decelerating with times the time that you're decelerating is negative 29. But then what else do we know to be true? So basically I'm using every fact that I know from this problem. I want your final velocity to be same as that car's. Notice the problem doesn't tell you that though. The final velocity should be the same. But you should be able to tell that it should be, because if your distance of closest approach is 15 feet, what does it mean to say closest approach? That means you're going as fast as that car, right? After that, you're gonna be, once you establish that speed, your distance is not gonna change. So the other thing that we know is that your position is 15 feet less than the position of that car at that instant, right? So the position of car A, X final of car A is X initial of car A plus V initial of car A, T plus half AT squared, right? So X initial of car A is what? 0. X final of car A is equal to V initial of car A, 88T plus half AT squared. In other words, this equation gives you this quadratic equation. The equation of this equation right here. 88T plus half AT squared. Now, what's the equation of this equation? Of the straight line equation. Then X final of car B is what? X initial of car B plus V initial of car BT. The acceleration of car B is 0, right? So the acceleration of car B is 0, and then so what? So that's it. This is the only thing describing that straight line position, you see? So then I have X final of car B is what? X initial of car B is what? 120 plus the velocity of car B, 58.6667 T. So this gives you the equation of this straight line, right? And then this gives you the equation of this guy up to this moment, right? And then we know that at that time, let's call this time T1, right? So this is gonna be what? A times T1. Right? So we know that at that time, A times T1 is negative 29. And then we also know that the difference between them is what? 15 feet at that time. So at T equals to T1, X final of car B minus X final of car A is 15. So take the difference of these two guys. Minus 88 T1 is 15.
How'd you get rid of the T on the 88 T?
Which one?
How did you get rid of the T?
I just subtracted this minus this is negative 29, and then A times T1 is that.
I know, but the top of the T, the initial T, right?
This one?
No, that's
The initial plus
my
AT.
bad.
Oh yeah, yeah. Okay, so then you're gonna have this. We can combine these guys, right? 120 plus this minus this is gonna be what? 58. Oh, that's the negative 29 again. Negative 29. 0.333 T1, and then negative distributes into this, and you get what? Negative half a T1 squared, that's equal to 15. You see? So what I know from this equation, I know that the difference of their distances is this. From that equation, I know that at that instant, they're going at the same velocity. So I have to combine this equation with that equation. Right? So then you're gonna get, how do I combine that?
Solve for T.
Yeah, I could solve probably, the best way is, I think it's better to solve for A and put it where the A is. Because if I solve for T, then I've got two places to plug it into. I'm lazy, right? I'd rather place it just into the A. So I'd rather say A is negative 29.333 over T1, and then plug it where the A is over there. Okay? Then A is gonna be, oh, then there's another negative here, right? There's a negative there, then there's a negative there, right? So negative half, and then this A is gonna be negative 29.3333 over T1 times T1 squared. And the two negatives cancel. And then T1 cancels with T1 squared, then 29 over 2, right? So then what is that? Divide that by 2, 14.66, so 14.66667, T1 cancels T1. Okay, then what? Okay, then I can take the 15, bring it to this side. Right, you get 105. Then take this guy to the other side, 29.33 minus 14. You get 14.66 T1, right? And then divide that by that. T1 is going to be 7.159. So that means this, your deceleration phase is gonna be 7 seconds. Right? And then once 7 seconds is elapsed, you're gonna be going at the same speed as the car. And then now we take that t and we put it back into this guy, and that tells us the deceleration, right? A is equal to 29 over that. Oh, not meters, sorry, feet per second squared, right? Is that what you were looking at?
No, but I think you can't guarantee that A doesn't change.
Well, we're assuming it doesn't change. In real life, yeah, you're gonna adjust your deceleration, you're gonna look at the car, you're gonna say, oh, maybe I'm decelerating too fast. Yeah, in real life, it's gonna change. But I'm assuming you just press the brake and you hold it.
It's a constant.
It's constant. And if it's constant, that should be the acceleration. So why don't you review what we did? So assume that it's just fresh. See what I did. See what if the graph makes sense to you. Yeah. Acceleration should be negative. Which one? Oh, this one here.
So when you plug it in on the right of the problem,
Oh, here you mean I had it as positive.
on the second. Like it's from the picture.
Yeah. Here you're saying this is positive. Is that what you mean? This is positive?
No, I was talking about the right. I was asking why I was
Here?
yeah. The what the
Well, because A is negative 29.33. Let's see here. He's saying why is the A positive here?
why is the positive?
Depends how you're defining the A. If I want to put negative AT, in other words, if I'm assuming that it's a negative acceleration, negative AT, then I also have to put a negative here. Negative here. You see what I mean? So he's saying, why did you set it up as a positive acceleration when you knew that the car has to slow down? What you could do is assume this is negative, but then you would also assume that this is negative. And then your answer would come out positive 4.9. You see, for the A. Then you would say the car has to slow down at the rate of 4.097. But if you put this as positive and this as positive, then the answer comes out negative. You see the difference? It's okay, either way. If you put both of them negative, then the A comes out positive. Any other questions?
Can I make an announcement?
Huh? Yeah, oh yeah.